All right, I'm pleased to introduce stranger to no one, hopefully, Eli Dart from ESnet, and he is going to be talking about the Petascale DTN project and his work with modern research data portals. So go ahead, Eli.
Hey, hello everyone. I'm going to talk a bit today about a couple of things. One is, as it says in the title slide here, the Petascale DTN project. And the other is the Modern Research Data Portal. And the one kind of builds on the other. I thought these were a good combination of things to include in a talk. Let's see if I'm able to actually advance slides. So I'm going to talk about Petascale DTN first, and then I'm going to talk about the data portal piece and wrap up a little bit with sort of a bit of a strategic look about where this might actually go. So this picture, I think, is likely to be familiar to most or all of you, right? This is the minimal sort of abstract cartoon of the science DMZ that has all the sort of the minimal diagram that has all the necessary pieces in it, right? The thing that I think is useful in the context of this talk is to think about what the science DMZ means in an HPC facility. So in this case, there's the sort of combination of the science DMZ design pattern along with a pretty common way of building an HPC or cluster capability, which is there's a parallel file system in the computing center that serves for multi-user storage, right? So this is something that users typically have an allocation on. They have a quota or something like that. And this is, a multi-petabyte file system, Lustre, GPFS, something like that. In some cases, it's NFS. But in the higher performing cases, it's often Lustre or IBM's GPFS, which I guess is now Spectrum scale now, or anyway. And this gives us two things, right? One is it's mounted by the compute resource, which is great. And it's also mounted by this cluster of DTNs here. And you can really think of the DTNs as the external facing API interface to this parallel file system. So we don't hang the parallel file system directly off the Science DMZ switch, but instead we front end it with this cluster of DTNs. And the DTN's job is to speak the transfer protocol or the transfer API of whatever tool set or data transfer platform you're going to use in order to transfer the data. And translate that into file system calls. So their job is to read files off the file system, bolt it onto a socket that the data transfer platform instantiates, and push that out using the data transfer API to someplace outside. Now, when you ingest data in this way, the nice part is there's no double copy workflow here, right? Write it out to the file system. It's immediately available to the computational resource, and more importantly, a user job running on that computational resource so they can launch their job against the data after the transfer completes without having to do anything else to it. So that's going to be some central context for the other things that we're going to talk about here. So if we build on top of that now, right, we can say, okay, we've got this enhanced cyber infrastructure substrate now, right? So we in the network world, we've been building big networks for a long time. We now have science DMZs connected to those networks, which is an absolutely fantastic development that's happened over the past 5 or 6 years, in no small part due to investments made by the NSF. And those science DMZs have DTNs in them, which is great. And those DTNs serve a bunch of different purposes for a bunch of different projects. Many of them are HPC facilities. Some of them are single PIs. Some of them are connected to data acquisition systems, whatever. But that's all a bunch of pieces. What the scientist actually sees is a data transfer application or a data transfer platform running on something, right? It's running on a computer somewhere. In some cases, it's running on the DTN. In some cases, it's running someplace else. But this allows them to do their data transfers. Maybe this is a data portal that allows them to search for and access data. Maybe this is a tool set that allows them to do data analysis. But these science applications are actually the user interface to all of this other cyber infrastructure stuff And so we have to think about that, right? In order to make this cyber infrastructure stuff useful and available to scientists, we have to build these larger structures on top of the components that integrate all these components together and make them into a useful scientific tool. So this talk is about data portals and the Petascale DTN project. Before I get into Petascale DTN, I'm just going to talk a little bit about data portals and show you what I mean when I say, air quotes, data portal. So say I have, and I'm a climate scientist, say, right? So I'm a climate scientist. I have this compute allocation at, Oak Ridge. Right, I'm going to do some data analysis there, and the data that I need for my data analysis is not stored at Oak Ridge currently. It's stored at NCAR because NCAR has this big repository of climate data. And so what I want to do is I want to take the data from wherever the data is and put it in a place where my analysis job that I have permission to run, because remember, that's where my allocation's not at NCAR, right? My allocation's at Oak Ridge. I want to put that in a place where the data is accessible to my data transfer my data analysis application. So, okay, great. I'm going to pull that down to the OLCF. So what would that actually look like? So I go over here to the NCAR RDA, and I get this thing. And so here we have this research data portal. Right?
So Eli, one quick comment, maybe make that larger and increase font.
Okay. Well, you mean you actually want to be able to see the content? I'm shocked. Shocked I am. So, is that better? Hope so. Okay.
Yes, sir. Okay.
So this is a web interface to a bunch of data, right? If you look at this, there's tons and tons and tons and tons and tons of data sets. Some of these are pretty famous, right? Like they have the whole 20th century reanalysis project here. They have a bunch of stuff. And so if I want to search around for data, I can do that. Right, and I can say, okay, well, let's look for different types of data, maybe some gridded data or something. And I'm going to go look around for some stuff. And it's all these different types of things, right? And I can sort of scroll through these. Let's look at this one. So this data set's got a DOI. It's got some stuff talking about the data set, time range for the data set. If I wanted to cite the data set, right, down here at the bottom, right, this is all the stuff that I would use to cite the data set if I was going to use this. It tells me how big it is. It's about 1.5 terabytes. And it's in netcdf format, which is typical of the climate community. So, okay, great. This is the data set that I want, so I'm going to grab this thing. Now, I could do this the old way. Right? And I could look at this and say, okay, well, here's the web interface, right? There's 1,100 files in this thing, and I could click on each one of these with my web browser, and I could try to grab them. I mean, this gets gnarly, like really quickly, right? I mean, look at all this goo, right? So I could do that, or I can do this. If I click on the Globus button, generates me a Globus job. And it's already there in the left-hand side of this here. So what I need to do is figure out a place to put it. So I'm doing my analysis at Oak Ridge. I'm going to navigate to the place where I'm going to put my data at Oak Ridge. Hey, why didn't you give me the listing of the data, you? This worked earlier today. All right. So I'm going to try this one more time, and if that doesn't work, I'll grab a different data set to show you. How irritating. Okay, well, let's see then if we can find a different one. Is it this one? Yeah, so this one's almost 0.5 terabyte, so it's not as large, which isn't as fun. But there it is. And we can go over here and grab this. You know what? I don't think I want to put it there. Oh, I want to put it here. So let's create a directory for this. And this is, an NCAR data set. So I'll call it NCAR. And select all the files. Drop it in. All right, light is green, the trap is clean. So now we can get on with our lives and talk about the Petascale DTN project. So the Petascale DTN project is built on top of the Science DMZ model that I described a little bit ago, in particular the notion of the Science DMZ design pattern as applied to a supercomputer center. The goal of this was to improve data transfer performance between 4 supercomputer centers. Right, so these are the DOE Oscar-funded supercomputer centers, the one at Argonne, the one at NERSC, the one at Oak Ridge, and then also NCSA. And there are a large variety of projects that use those computing facilities, and so this is one of those things where if we can get this right, it's going to help a bunch of different projects. The performance goal was to be able to achieve a data transfer rate equivalent to a petabyte a week, and so and I guess the other goal too was to not have the user have to jump through a bunch of crazy hoops in order to achieve that performance level. And so that's why we used Globus instead of something else. So we had a reference data set, and I'm going to talk about where we got that reference data set in a minute, but it's about 4.4 terabytes of simulation data from a cosmological simulation that we got from a scientist. And the goal here is to use all the production options, right? So that this isn't, pardon my vernacular, lies, damn lies, and benchmarks, but this is like, for real stuff on multi-user resources to show what a user would actually get if they actually decided that they wanted to actually, do this. So where did this idea come from? We had a CrossConnects workshop for Cosmology in 2015, and Salman Habib from Argonne gave a keynote there. He talked about the large cosmological simulations that they had and some of the workflow challenges that they were encountering dealing with those data sets. So they have, very large, petascale data sets. So they'll over a period of many, many months, they'll generate this very large body of simulation data. And then what they want to do is go and cross-cut through that data set, right, and then analyze pieces of it in relation to whatever a particular project might need. So there's a couple of different components to this. One is a sort of petascale data replication workflow, and another is if I want to stage a portion of that to some supercomputer center for analysis, I want to grab a slice of that, which is on the scale of tens to hundreds of terabytes. But what I want is to be able to move the data sets on human reasonable timescales, and I want to not have to babysit the individual components of the transfer, right? So, busy work is the bane of a scientist's existence, right? So we want the computers to handle the complexity of dealing with all that. And so why did we have to have a project to do this? Well, if you looked at the way things were at the time, the data transfer rates between these different HPC facilities were low. They had multiple Globus endpoints. It wasn't clear which one that a given user should use. And the configurations across the DTN clusters weren't consistent. Now, there were high-speed networks connected to all of these, but inside the center, the infrastructure wasn't consistent. And then, as I mentioned earlier, right, so Cosmology isn't the only group that needs this. There are a lot of other scientific fields and collaborations that are going to need these sorts of capabilities. So the idea was, okay, let's use this as a pilot to figure out if we can get this solved for a large number of scientists and collaborations. So this diagram shows where things were sort of in March of 2016. And, so remember, we're going for performance equivalent to a petabyte a week, which is a little less than 15 gig, but for, round numbers, call it 15 gig. And the nice part there is if someone wants to move tens of terabytes or maybe even 100 terabytes, that's going to happen in a day or two, right? If you can do a petabyte in a week, it's going to be pretty easy. And this isn't something that somebody's going to have to spend a lot of time on. So if we look at the performance here, it was kind of variable. Some of it was close, some of it was demonstrably not. And so we, went to work on it, right? This is a performance engineering problem. Great. Let's go and do this. So by May, we had things working pretty well between NCSA and Argonne. Some of the other things weren't doing so great, but you do what you can. And I'll talk a little bit in a minute about some of the things that the different centers did to improve things. By October, we had made some really significant improvements in other places. So if you look at the performance there between NERSC and Argonne, it was doing pretty good. Argonne to NCSA was rocking. But we had developed a problem in the NCSA to Argonne direction. Okay, so that gives us some. So remember, this is a complex multivariate situation. And so you have to just keep drilling down, find the problems and fix them. But where we ended up late last year was someplace that's pretty nice. So if you look at the diagram here, so the green, the blue, black, and red, there are min, average, and max of 3 tests for a given direction. And so we're ranging, for minimum transfers, right? The lowest one, we're in the 20 plus gigabit per second range. At the top end, we're over 50 gig. I mean, so there are 1, 2, 3, 4 of these that have a max of over 50 gig. Now remember, this is production, multi-user infrastructure, real simulation data set with all the production options turned on, including checksum verification. Oh, and I should say, if you look down in the lower right here, this actually shows the composition of the data set. So it's about 19,000 files, couple hundred directories. And the files range from, 0 bytes. I mean, those are probably control files or something. I don't know. I didn't actually go and dig through all 19,000 files to see what was actually in them all. I wouldn't understand it anyway, right? It's astrophysics simulation output. I'm not an astrophysicist. But if you look at the file size distribution there, it's pretty broad. There are a bunch of different sort of sizes of files. And so, this is sort of a proper test. It's not like I'm going to transfer the exact number of files that are all exactly the right size in order to make things line up beautifully, right? This is a huge bag of goo that we're throwing at the transfer platform to make it just do the right thing for us. And that's what it's doing. So over the life of the project, several improvements were made by the centers. There were some tuning things which I haven't really articulated here, but they expanded their DTN clusters, which was nice. NCSA did not expand theirs. They already had a gigantic DTN cluster. They still do. I think it's like 28 DTNs or something like that. It's significant. Oak Ridge also has a large DTN cluster. They break it into several different pieces, so they have function-specific pools of DTNs. So they've got several that they devote to their Globus endpoint. They have some that they use for HPSS. Some are wired into the job scheduler, and some are used for interactive use, and SSH to it and run rsync or something if you're still stuck, back in the dark ages and having to run rsync for something. Some network upgrades were also done. And there was a sort of unexpected benefit along the way. Globus changed their the way they managed transfers with very large file counts, and that gave us some efficiencies as well. So all that put together, we did a pretty good job. And so at this point, we now have a capability across all those HPC facilities that is available to any scientific project that needs to move large amounts of data between those facilities. And it turns out it's also useful for things like data portals, which I'm going to talk about next. So what is a data portal? So I showed you an example of the NCAR data portal a few minutes ago, but if you just thinking about what a data portal is, right? It's a large repository of scientific data of some sort. These are typically devoted to a project or a field. So the NCAR one's got a bunch of climate data. Some of them associated with astronomy and cosmology. They're going to have observational data or astrophysics simulation data, something like that. There are some for biology, genomics, et cetera, et cetera, et cetera. And so, they provide access to data sets for scientists. I mean, that's sort of their function, right? Is for a scientist to be able to go and find the data that they want and get access to it. So they have browsing, search, all those kinds of things. Now, if you think about where the data portal idea came from, so if we go back to, you know, the late 90s or, you know, Y2K-ish, around that time, the Apache web server sort of got good. Now, remember, we had, as the state of the art, right, back in those days, it was command line FTP, right? And that's what we used, and it was useful, but that's what we used. And around that time, Apache sort of got good enough. We got CGI programming, so you could sort of build dynamic web pages. Database integration started to get good. And suddenly you have all the sort of components that you need to build something better. So you can have a database for metadata. You can manage some users in there, integrate it all with CGI programming. And by the way, you scientists don't have to build a GUI because somebody else has already built a GUI for you. It's called a web browser. And somebody else even maintains it for you, and it accesses your data portal using standard protocols, right? All you have to do now is give your web server a file system mount so it's got access to the data objects, and voila. You have a GUI that gives you access to different portions of your data set depending on your search criteria. And that's spectacular, right? So way, way better than the state of the art at the time, which was command line FTP. And so that's where the data portals come from. The architecture of a data portal has essentially not changed in the 15 plus years since, you know, Y2K. I guess that's, you know, 18 years since Y2K now. And it's still the way it is, right? We still have a web server that's got a file system mount. And it's dragging all those data objects up through the web server in order to hand them to you. And it kind of looks like this, right? So you've got this web server stuck someplace. It's pulling these data objects through it. And we all know that Apache is incredibly high performance when dealing with terabyte scale data objects, not. And in fact, you know, those data objects, they've gone up in size by a couple, 3, 4 orders of magnitude since that time. And so if we say, okay, well, what we'd really like to do is drop this thing into a science DMZ to make it go faster, that's a problem too. And the reason that's a problem too is, what is a data portal, right? It's a somewhat complex database-driven web services application. What's a really nice sweet spot for security vulnerabilities right now, and for the past like many years? It's complex database-driven web services applications. And so you need to monitor for SQL injection, you need to monitor for all kinds of stuff that the security model of a science DMZ is actually ill-suited to defend. So we can defend a simple data transfer API with ACLs in a science DMZ. We can't do things like monitor for SQL injection. Now you can if you want to stand up a big bro infrastructure and things like that, but that level of scale and complexity requires that you have a couple of FTEs to do that, and that's out of reach of many sites. You know, so for defending a application like this in a science DMZ environment. So, okay, so we can't do that either, and even if we could, right, we're still dragging it all through a web server. I mean, really. So let's think about how we could actually do a better job. So what we need to do then is re-architect this thing. So if we want to re-architect something, right, what kind, and I'm not talking about just sort of change a couple of things. I'm talking about really rethink the architectural design of this thing. So let's, as an example of the level of architectural design that we're talking about, let's look at what happened with content delivery networks back many years ago for the web. So what's a content delivery? And I'm not necessarily saying that CDNs are the answer to science data distribution, right? This is an example of architectural change, not promoting an architectural model for data portals. I'll get back to that in a second. So what do we do with CDNs, right? The idea is to store the content, right, the static data objects in a separate location from the dynamic content. And the reason for that is static content is static, right? The complexity is in the dynamic piece. And so if we can separate those two, we can optimize those two each. separately. And it turns out that that's sort of the web model of serving things is really amenable to this. So if we look at the way it used to be, right, you'd have all your content on a web server. And if a browser goes and pulls the data out of that web server, the data comes from the web server. It traverses some set of networks to get to your web browser. Now, if that's close by, that's great. If it's not close by, that's not great. And in fact, all of the content inherits all of the features of the entire path between the web server and the browser. So what do you do? Let's take those things apart. Because remember, I mean, if you look at the structure of a web page just says go and load this image or this data object from this other server. Well, from this other server can be this thing sitting quite close to you, browser, in a colo quite near your residential broadband network, for example. So that's great. Latency goes down for large data objects. Time to page render goes down. And it's a real big win for web application performance, because the only stuff that's traversing those sort of long distance path between the web server and the browser is a few small, essentially text files, right? A web page is a text file. So that's fairly small and easy to do. So the other nice thing about this is the client doesn't have to be modified at all in order to do this, right? The client doesn't see this CDN as a separate thing. It just sees that there's a web server out there on the net and I load some content from it. What's actually happening is this other thing, but that's transparent to the user. So this is not a brute force solution. This is work smarter, not work harder, and that's great. So if we want to do the same level of rethinking of a data portal, what do we need to do, right? We need to disassemble the thing and look at all the different pieces of it and try to figure out, okay, what is it that we're gonna do with these things? How can we put them back together in a saner and more performant way? So we've got a bunch of functions, right? We've got search, we've got query, we've got a data download method of some kind. Maybe we need to support more than one. We've got a GUI, right, so that humans can access this thing. And ideally, we'd have a machine consumable API for access to that data as well. Now, where's the performance pain? It's in the data handling part of this. And I mentioned before, over the course of the past 15 years or so, we've seen the data objects go up in scale by a significant amount. That is likely to continue. So whatever we want, we want something that's scalable. And we want to be able to use the science DMZ model so that the data transfer portion can actually be optimized in a sane way, and we don't have to run up against our security model by putting complex applications in a science DMZ. So what does this look like, right? So here's our old data portal design, right? And this is where we drag everything through a web server, and then the traffic out of that web server gets dragged through whatever portion of the network and through the firewall and all the things that we don't like for sort of large scale data objects. So instead, if we place the data objects on this DTN cluster, well, on this file system front-ended by a DTN cluster, now the high performance stuff happens on something that's already optimized for the purpose, and that's great. And we actually have there's a paper on this. There's a link there at the bottom of the picture and also at the bottom of this slide. So what we've actually done here is we've separated the data handling piece from the portal logic, right? So the portal is still its portal-y self. It's still a bunch of web pages. It still has search. It still has all the things in it that it had before. It's just that when you, scientists, decide that you want to select some data objects, instead of handing you a pointer to a data object that points back at the data portal itself, right? Instead of pointing back at the web server, it points over there to a data transfer cluster in a science DMZ that's been optimized for the purpose. Now, the cool part about that is I don't have to change the data portal at all to scale up the performance of the data transfer piece. I want to add more DTNs, I can do that. I want to add more file system, I can do that, right? And if the location for the data changes, I change the name of the endpoint in the data portal. I don't have to change anything else, and it all just points over there. So we've outsourced now the data handling piece to a data platform that runs in computing centers, and we can outsource the storage to the computing centers who actually know how to do it. which is great. So this is the performance that I've seen out of the NCAR RD. Oh, I have that transfer. Let's go see how did we do here on that transfer? Okay, so while we were talking, so it's not quite a half a terabyte, but it's close to a half a terabyte. But it moved in 5 minutes while we were talking. And I didn't have to do anything other than start the transfer, right? And it ran at about 1.5 gigabytes a second. So that's like 12 gig ish, something like that. I've gotten 2.5 before. Again, this is multi-user production infrastructure. So I'm just there like anybody else doing whatever anybody else would do. But you know, this works to first order. So, well, now what's the long-term vision of this thing? So we have a bunch of different data repositories, data sources. Some of these are synchrotron facilities. Some of them are computing centers. Some of them are, you know, tokamaks fusion reactors. There's a whole bunch of stuff here. And all of these things are connected to the science network that serves them. So, you know, if we go around the ring here, there's a bunch of DOE stuff up there in the upper left. There's, you know, NCAR, NCSA, in the upper, and so forth, San Diego up in the upper right. Commercial clouds are being used more and more for scientific computing. And then if we look at the lower left, we have other federal agency networks in the United States, NIH, NOAA, NASA. But then we also have all of our collaborators around the world. So there's a few example things there. NCI in Australia, the Bell 2 experiment in Japan, CERN Square Kilometer Array, and so forth. So all of these things are connected to their science network. And the thing that we're working towards here is an environment where the data handling piece of this is all connected to this high-speed network backplane, right? And the data orchestration can happen wherever the data orchestration needs to be, but we've got all of the connectivity and all of the intelligence inside this sort of data plane for the international science complex. And so this allows us to move data between data portals, between, you know, from experiments to HPC, between universities, out of the LHC experiments to wherever they're running this week. They run all over the world. So that's the state that we're working towards here. And this data portal notion is an important part of that. And the Petascale DTN project and things like it provide us with the substrate to build those larger structures upon. So I will stop there, and I'd be happy to take any questions that anybody has.
So thank you, Eli, for going through that. We'll wait a minute or two for questions to come in. I sort of jotted a couple down as you were talking that I can start off with.
Okay.
So I guess the first question that I have is, you know, sort of the vision statement right now is sort of single application focused, you know, based on top of Grid FTP and Globus. How challenging would it be to adapt this model to allow other applications to sort of use it if we're, you know, a little bit more big tent and we have other new applications that are coming online or some of the old ones that people may be forced to use?
Sure. So I think the way, so the design pattern of the portal is platform agnostic. Right. So the thing that you need in order to build one of those portals is a data transfer platform that provides you with the ability to orchestrate the data movement and provide hooks for that orchestration in whatever your web-based data portal is. Right. So you need a way to take whatever collection of data objects you've gotten out of the database in your web portal and hand them off to whatever that data orchestration platform is. And I mean, I chose Globus in this case because Globus is running at all of the places that we were sort of including in the test. But you could do this with any platform that has those necessary components, right? And so, the necessary components there are a machine consumable API for moving things around, high performance stuff that can be deployed on the DTNs, and the webhooks that go in the data portal, and an orchestrator that allows you to do all of that, to do all of the data movement pieces and checksumming and failure recovery and all that stuff without involving a human in those things, without scaling up the human effort with the scale of the data set. So this could be any platform that you wanted. I chose Globus in this example, but if you had a different platform you wanted to use, you could do that as well.
All right. So we've had a couple of questions come in. Some people are sending them to me privately, so just if you want me to be public with the question, please specify. George Robb says, is there a difference in performance for IPv4 or IPv6 in this system that you've seen?
So as far as I know, Globus doesn't do IPv6 in their cloud-based data transfer service. I would encourage you to talk to the Globus folks about that if that's something that is of interest to you, and just sort of see what their roadmap is. In other data transfer applications, and certainly in our Sonar infrastructure and things like that, I haven't seen much of a performance difference in v4 versus v6 at this point. Every once in a while, we'll still run into routing anomalies for v6 where people just haven't, where the v4 network and the v6 network aren't necessarily congruent. But that's not an application performance issue. That's a network engineering issue. And when we find those problems, we fix them. I haven't seen one in ESnet for a while, but those do still crop up a bit.
Okay. Kevin Thompson wants to know, the last topology shows data exclusively behind DTNs on edges. Why can't exchange points in the core integrate storage and compute in the future?
There is no reason at all that exchange points could not do that. And in fact, there are a couple of projects being done by people sort of associated with the LHC experiment. So this is people like Sean McKee and Rob Gardner, who are looking at precisely this, right? So can you take a cache, right, just a DTN with a big bag of disk on it, stick it in a Science DMZ somewhere, where that Science DMZ may be in a telecom POP, it may be at an exchange point, it may be at a university site, it may be, wherever it happens to be, and just have that thing speak the machine consumable API and nothing else. And the answer is that's a fantastic way of distributing data into places where it might be, say, close to an OSG cluster. So say, for example, you had a bunch of different campuses that were part of a state university system. So, here I am in California, right? So say we had a bunch of UC campuses here in California, or maybe I'm in Texas, right? I have a bunch of the Texas universities or whatever. I mean, there are lots of these state university systems that are glued together, as all such things are, by their regional network. And it could easily be the case that the regional network stands up a storage capability and says, okay, we're going to make this available to the OSG clusters because the different campuses that are running those OSG clusters don't have the resources to stand up their own storage, but we, the network, will do that, and will provide just the API that speaks to this thing. Nobody gets to log into it but the sysadmins. And all it does is throw data on the wire in response to properly authenticated API calls, right? That all makes a lot of sense. And there are people working on doing that now. I wish I could remember what Sean and Rob's projects are, but I'm pretty sure that they are, but they're working on these, and I think that they're
Hi, Eli. This is Sean. I'm on.
Oh, hey, Sean, go for it. What do you got?
So there's stash cache, right, which is an attempt to make a transparent cache on a tuned up system so that the end users don't have to know that it's actually there. It's similar to the concept of content delivery network. And you strategically locate those, as you mentioned, to benefit users who need to access distributed data. And so the attempt here is to try and couple a few things together, well-tuned end systems, reasonable storage, and do some work where the user tools then can transparently take advantage of those caches. We're also experimenting with sort of point-to-point work with software-defined networking to see if we can help expedite things in certain circumstances, shape flows, and make the flows much nicer on the backbones and such.
Excellent. Thank you.
All right, so I have another question here that somebody sent to me, and it's related to my initial question on alternatives in the application space. Kurt wants to know or points out that he has researchers that balk at using Globus when they work with people in business and industry, namely because of, cost and things like that. Are there any alternatives that you know of that could work in this space?
I don't know of other sort of full-featured platforms. I mean, there are commercial, data transfer tools, but if cost is an issue, I don't know whether they'd want to pay IBM for Aspera, for example.
And
yeah.
George has pointed out at the same time BBCP, which, George, you're right, it is used at a lot of other facilities as well. I mean,
right.
the environment is rich with these things, but it all comes down to feature set.
Right. So I think it's useful to take a little bit of a side trip here to talk about sort of the difference between an architecture and a tool and a platform. So for an architecture, we have something like the Science DMZ model or the Modern Research Data Portal design pattern or something like that. Right. And that's sort of a framework for doing things within which you can instantiate pieces of cyber infrastructure that work for specific purposes. You can run a tool on a DTN. You can run any tool that you want. It's just a Linux box, right? You can do whatever you want, whatever meets the needs of your users and your policies. But command line tools, right, where it's just a binary that I type a command in an SSH window and I run, those have limited scalability, either in the sort of size of the data objects that they can handle. So this is like wget or rsync or things like that, or in the amount of human effort required to make the thing do the thing. Right. And so, yes, BBCP does work if you know how to use it. That's great. And there are other tools in that space too. I mean, legacy grid FTP works great as long as you know how to drive it. What we're finding is at human scale, there is a decreasing appetite for individual tools that require a large amount of sort of CLI level expertise on the part of the user. And so that's when you start getting into what I would call a platform, which is something that has more features, right? And it has the ability to do orchestration. It's got an API that allows it to be integrated into the other parts of the cyber infrastructure, whether that's the control software at a beamline or, as I just described in the data portal piece, the integration with the search and other functions in a web-based data portal. And those platforms require, they have a lot more functionality and a lot more capability. They also require human effort to maintain. And so it's difficult, I think, to build those platforms just on the open source model. Now, I will say there are some, OSG is one. And they've managed to come up with a pretty hefty software stack that allows them to do data orchestration and things like that. The LHC experiments have their stack as well, and they sort of have sufficient free energy within their collaborations to do that. Most scientific collaborations in the world don't have the human scale to do that. And so they need to somehow be able to incorporate the capabilities of something that has the features of a data platform, without the sort of human complexity of using individual tools. And there is a tension there. I won't argue with you at all. And this is something that the scientific community is gonna have to figure out. But I think that it's something we're going to have to figure out. And my guess is that, you know, if I'm an HPC facility, I'm going to have to support individual tools, and I'm going to have to support platforms within the architectural context of my HPC facility and my science DMZ and so forth, for the foreseeable future, because that's just what I need to do to be able to support the N thousand users that use my HPC facility.
Okay, so good discussion there. Anybody else have any questions or comments different from what we've gone over here? We'll give it a minute, and while I do, I'll thank Eli again for his time today.
Delighted to do it. Yeah, it's great to talk to everybody.
All right, so I'm not seeing anything else pop up. So thanks again, Eli. For those still on the call, the talk next week will be from Marla Meal, Wendy Huntoon, and probably Kate Mace or Lauren Rotman, I'm not sure, on WINS.
Excellent.
And that'll be at the same time, same place. And we're going to have a 1 week break after that. And then I need to start lining up people. So open call that if you have something or know somebody who wants to give one of these talks, we need to start getting them in here. Otherwise, it'll be a boring couple weeks. So thanks again, everybody, and have a good weekend, and we'll talk to you soon.
All right. Cheers. Thanks, everybody.